Hi, this is the second video of the series. In the first video, we had some introduction about the different things that we could see. Now I'll move to joins. Now my idea here is not to go in details into any of these topics because of course these are tricky topics, but to help you understand a general idea about what they do so that you can then take these things on your own. So SQL joins are used to query data from two tables. We have four joins here: the inner, outer, left, right. If you want to remember the names, inner, outer, left, right. The inner join, it is the simplest of all join operations. Inner join returns all rows from multiple tables where join condition is met. There must be a matching value in a field common to both tables. Inner join cannot be nestled inside a left, right, or join. So it creates a new result table by combining two columns, column values of two tables based upon the join predicate. Join condition determines whether both records are matched or not. If there is no match found, no record is returned. So loan inner join borrower on loan dot loan no is equal to borrower dot loan no. So just an example here. So the result of this join would give us the output based on the common row. So if nothing occurs, then we don't get anything. Then we have the natural join. The natural join combines two databases based on their common columns with the same name. Therefore join condition is hidden and dependent on table structure at runtime. This obviously creates potential future danger. As soon as the table changes, results may become unpredictable. Yes, yet syntactically correct. It offers a further specialization of equijoins. The join predicates arises implicitly by comparing all columns in two tables that have the same column name in the join tables. The resulting join table contains only one column for each pair of equally named columns. As previously noted in the relational algebra that we have been doing, that this operation when performed forces an equality on attributes which are common in the relation specified. If we take a natural join of borrower and a loan, then equality is forced on attributes which are like the loan and the natural join borrowers. The only attribute common to the two fields, the result of the expression is similar to the result of the inner join that attributes only once in the result of the join. So a little bit about the left and the full join. So the left join, rows satisfying selection criteria from both join tables are selected, as well as all remaining rows from the left table are kept along with null instead of actual right join table values. As we can say, it returns all values from the left table plus match values from the right table, or null in case of no matching predicate. If the right table selects one row and the left table return more than one matching row for it, the values in the right table will represent each distinct row on the left table. And then we have the full outer join. The full outer join is a combination of left and the right join times. As a result of inner join is computed, tuples from left hand side relation did not match with any of the right hand side are extended with nulls and are added upon to the results. Similarly, tuples from the right hand side relation that did not match with tuples from the left hand side of the relation are also extended with nulls and are also added to the result. So a little revision here, it's similar to VLOOKUP, and there are four of them that are often seen. So the full outer join is a combination of left and right join. The inner join returns all value from multiple table where the join condition is met. Natural join combines two tables based on their columns, that is column with same name. So that was about the join. We now move to entity relationship diagram. So entity relationship diagram allow us to describe data involved in real world enterprise in terms of object and their relationship, and is widely used to develop an initial database design. The ER model is important for its role in database design. It provides useful concept that allows to change the detailed and information description of what user wants, and we want to be precise and have formal description that can be implemented into the database management system. Within the overall design process, the ER model is used in a phase called conceptual database design. Even though the ER model describes the physical database model, it is basically used in design and communication of the logical database model. The overall logical structure of a database can be expressed graphically. So we use relationship, entities, and attributes. So we have got four types of block in these kind of entity relationship diagrams. We have rectangles, which represents the entity. The diamond represents the relationship among the entity sets which are connected to the rectangles by lines. Ellipses represent attributes and are connected to the entities or relationship by lines. And lines link the attributes to entity and entity sets to relationship. So the labeled diamonds, ellipse are labeled with the entity, relationship, and attributes respectively, and they are labeled based on what they represent. The entity or the rectangles is a thing, object in real world that is distinguishable from other objects. For example, each employee is an entity and department is an entity. The diamond is as an association between the entities. So if we work on departments here, and if we have got something like department and employees and professors, then the relationship between two identities can be found out. So like a professor teaches in the department and the student learns from the department, something like that. So at last, each field has its own details which are represented by attributes. Like the employer might have their name, salary, department, and so on. Now we have constraints. So one employee can work in one department and one department can have many employees. So these are some of the constraints. We want to have only one employee in one department, and then this is an example of a key constraint. So the restriction that each department can have only one manager is an example of key constraints. This restriction is indicated in the ER diagram by an arrow, such that the department can have only one manager. Therefore, as there is no arrow from the entity, we can say that many employees to one relationship can manage. So we have to be careful about this arrow. So then we have to look at the ER diagrams. Now if we want to write an ER diagram for a company database which was based on a department or some financial data, we have to follow few steps, and I'm going to talk about 5 steps. The first step is identify strong and weak entity sets. So we have to be careful about that. So we have to define the entities. Then we have to identify the relevant attributes, and then we have to identify the relationship set, all meaningful relationship between each set. And then we have to identify cardinality ratio, or is it an n to 1 or a 1 to 1 or a 1 to n or an m to n, which means that you can have one or more linkages, so that you can put an in there. So, and then you have to identify an is a or a has a relationship set. So an is a or a has a relationship set for a given problem. So there is no generalization here. Now there are many issues which are related to the entity relationship diagram, but the whole idea here is that you have to describe the entire data into something meaningful. If you want to look at in finance, this would be like a loan payment, and the loan, the qualities of the loan, again the payment and the market, and different attributes, so that when you update one, you have all things in the right way. So that is the whole database design using the entity relationship diagram. So that was one part, that you have to first you have made a design of what you want. Now there is something called the normalization or refinement process after identifying the identities. So the starting point of normalization process can be visualized as a universal relation. This relationship contains all the attributes of interest and is structured so that each tuple in the relationship has single valued element. Normalization results in formation of tables that satisfy certain specific countries and represent certain normal forms. And this was defined by E.F. Codd in the first, second, and the third normal form. The The third normal form is what we are going to focus, but I'm going to talk about a lot of them. So we are looking here at the defining of design for relational tables to minimize data redundancy. So we have got a bad data and we want to remove the redundancy and make it systematic. So normalization is based on the concept of normal form. A table is said to be particular normal form. It satisfies certain set of constraints defined for that normal form. These constraints usually apply to attributes of table and a relationship among them. There are multiple level of normal forms, each having a specific factors that could be reducing data maintenance anomalies. So we have different type of normal forms: first, second, boycott, BOYCE, fourth normal, and fifth. So three are important, but again boycott and fourth and fifth are the others. So if you put unnormalized data, you'll get the normalized data. You can imagine this like a funnel. The first normal data states that there should be no repeated groups in the column. In other words, column in each table should have atomic values. A column is said to be atomic if all values are indivisible units. The relationship R is said to be first normal if and only if each attribute contains atomic value. The table consists of atomic values if there is one evaluator for one given row and column intersection. Non-atomic values result in repeating groups. A repeating group is recurrence of data into a group of data items within record. So you want to really remove those groups from you. So you want to decompose that and create another data table. So the dependent column is having atomic values, and the repeating groups refer to a set of columns whose value are repeated and repeat in a table. So that should not be there. So that is the first part, and breaking down into relations would be the second part. So making sure that works. So if you are linking everything with IDs of people or whatever, then you have to make those two tables that are dependent. So table before the first normal form and table after the first normal form should be a clear and a clean one. Now let's look at second normal form. The table in the first normal form may show redundancies due to partial dependencies. This second resolves the partial dependencies. The second normal form states that the table should be first normal and every non-key column must be fully functional dependent on the primary key. And what we mean by here, and what is partially dependent? So an attribute column is said to be partially dependent if its value can be determined by any or more attributes of the primary key, but not all. Each normal form is built upon the previous normal form. The first states that the prerequisite for second normal form is to have its table in first normal form. The fully functional dependency is given a composite primary key, a primary key consisting of more than one attributes. Each column attribute, which is not the attribute of the primary key, should be dependent on each and every one of the primary key attributes. If the attributes depend only on a part of primary key attributes exist, then they are removed and placed in a separate table where the primary key of the new table is the portion of original key key that they are dependent on. A non-key attribute is fully functional dependent on the primary key if the functional dependent on the attributes comprising the primary key. So a relationship is said to be second normal if and only if it's first normal, and every non-key attribute must be fully functional. So we take it from what we do in the first and then we divide it, and the whole idea is this primary key one. So key remains the major thing here. So every data will have its key which would define that. So we have the table that the second normal form may again show redundancies due to transitive dependencies. So if you look, we looked at partial dependencies and now we are looking at transitive dependency. A third normal form resolves transitive dependencies. A transitive dependency arises when a non-key column is functionally dependent on other column that in turn is functionally dependent on the primary key. So it's like a dependency on a dependency. So you want to clean that up. So table should be second normal form and table should be devoid of transitive dependencies. Column dependents on other column that are in turn dependent on the primary key are said to be transitionally dependent. So the first rule for the prerequisite of third is again that it should be second, and of course for the second it should be first. So relationship is third normal if it has 2NF and every non-key attributes must be non-transitive dependent on the primary key. 3NF ensures that none of the non-key attributes are dependent upon another attribute, which is turn dependent on the primary key. So we have to break everything and make sure that this transitive relationship is not found. So that is like the normalization of data. In simpler words, if you were to look at it, we have got a lot of data, we want to clean that up for our work. So the first is to draw an entity relationship diagram, and then we have the normalization, and these two would form the chunk of things that you are going to do. I hope this was helpful. Thank you for listening.